Okay, so welcome back everybody. Hello, I am your new professor. Your old professor had to take a leave of absence, and now I am here today to teach you some lovely physics with new advanced technology and bright fun colors. So today we're going to be talking about magnetic fields. From your previous education, you've already learned that in gravity land, F equals ma, and in electric land, Fe equals QE. But how does that go into magnetic land? So we're going to be deriving the equation for the magnetic force today. So there's some things that you can derive pretty easily about it. Fe obviously corresponds to the magnetic force, which we're going to call Fb. And there is also a magnetic field, which we're going to call B. But we don't really know what's in this space over here because there isn't really a magnetic charge as there is an electric charge. So how are we going to figure that out? Well, first we're going to rearrange it so that B equals Fe over something. And B is a vector quantity, and so is, so that's that. So how are we going to figure this out? Well, we're going to do it this way because there's two types of ways to generate magnetic fields. The first way is through the permanent magnet, which is basically when particles themselves have magnetic fields. So like the magnets you put on top of your refrigerators, those are permanent magnets. But there's also other types of magnets called electromagnets, which derive, which make magnetic fields based on the movement of electrically charged particles. So what we're going to do is use that to our advantage, because obviously if there's movement of electrically charged particles, then there is both a Q and a V, and we're going to call QV the force magnitude. And since the V in this case is also a vector, and so is B, we're going to rearrange this so that the vector B times, or cross product of, Q vector V equals FB, the vector. So in the end, FB equals QVB. But see, this is a cross product, so that must mean that there are angles involved. Well, as I said, there are angles involved. Wow, amazing. And basically it's like this. So you have, if you have the field line, magnetic field line B over here, and you also have the vector velocity over here, and since there are vectors, there's going to be some angle in between them, and we're going to call that phi. Well, due to our experimentation, we know that FB must always stay perpendicular to the velocity V, and also must stay perpendicular to the vector B. And if you have this angle, then clearly they are not perpendicular, so we can only take the perpendicular component of that vector. So we can basically only use V sine phi. So we're going to put that in here as sine phi, and that's actually your final equation, which is FB equals QVB sine phi. And of course, now you may be wondering, well, what's the unit of the magnetic field? And that is, in fact, a Tesla, which is, of course, an old dead guy. Super smart, and this is 1 Tesla, which is actually coincidentally also equal to 1 over Newton coulombs meters over seconds, which if you know what an ampere is, that is also equal to coulombs over seconds. So you can make this into 1 Newton times coulomb seconds over m equals 1 n over am. So that is what the unit of a Tesla